Hey everyone, I'm Sudarshana. I'm student of Velu Institute of Technology, Chennai. In the 20th century, security was defined by mathematical complexities, which means number protected the information. In the 21st century, security is being redefined by the properties of matter, such as coherence, entanglement, and physical laws. This presentation explores that evolution. Cryptography comes from the Greek words cryptos, which means hidden, and graphia, which means writing. It's not just about hiding messages, it's about mathematically securing the information. Every time you send a message, log into a website, and or make a digital payment, cryptography ensures your data is confidential, unaltered, and verified. Confidentiality means no one else can read your message. Integrity ensures that even if someone intercepts it, they can't modify it without being caught. Authentication verifies who you are actually communicating with, that the sender is actually genuine. And non-repudiation ensures that once a message or transaction is sent, the sender can't deny it later, which is essential for contracts, payments, and digital signatures. All four together make up to the pillars of modern cybersecurity. Next is how cryptography works. Encryption and decryption. Encryption is the process of transforming my readable data, which is my plain text, into an ciphertext. Decryption is the reverse process of encryption, that is converting my ciphertext back to my plain text. Mathematical representation is I will represent my ciphertext in the form of encrypting my plain text. E is an encryption algorithm, K is my key, and P is my plain text. Similarly, D is my decryption algorithm. In order to send plain text, which is allowed after to my receiver, I'll be encrypting and sending it in order to increase my security. Over here, one important thing over here is that security depends upon the secrecy of the key, not on the algorithm itself. It's a principle known as Kirchhoff's law. Types of cryptography. Cryptography isn't just theory. We use it every day. In case of semantic cryptography, imagine Alice and Daphne using the same secret code word to lock and unlock messages. It's fast. That's why apps like WhatsApp or Signal use AES, which is Advanced Encryption Standard, a symmetric algorithm to keep your chats private. However, the major challenge over here is that both must already share the same secret key. In asymmetric cryptography, there are two keys, one public and other private. For it's one of the best examples for this is Gmail. Your public key is like your email address. Anyone can send you encrypted mail, but only with your private key. You can open it. Finally, in hybrid cryptography, both systems work together. For example, when you open a website starting with HTTPS, your browser first uses asymmetric encryption, such as RSA, to exchange a symmetric AES key, then switches to that faster method for the rest of your session. This balance of your security and efficiency, that is what keeps your online banking, shopping, and cloud data safe. Mathematics, the engine of encryption. When you encrypt something, you're not hiding it. You're transforming it into a form that only specific math can undo. RSA, for example, multiplies two enormous prime numbers to form n. While multiplying it is easy, factoring n back to its original prime is computationally infeasible. That's why cryptography isn't about secrecy. It's about math that's practically impossible to reverse. Over here, in a case of RSA algorithm, n refers to P into Q, where P and Q are two large primes. Security arises from difficulty of factoring n back into P and Q. So usually we take a larger n, which means larger P and Q. This is an example of an RSA algorithm. Over here, I have chosen P as 3 and Q as 11, which makes my n is nothing but 33. And I'll also be calculating Euler's torsion function. Phi of 33 is nothing but phi of 3 into phi of 11. 3 being a prime number, my phi of 3 becomes phi of, which is nothing but 2 minus 3 minus 1, which is 2. Phi of 11 again being a prime number, it becomes 10. In case of phi of p, for a prime number, my phi of p is nothing but just p minus 1. Okay, now I'll be choosing my e is equal to 7 and I'll be getting a co-prime number that is co-prime with which is co-prime with 20, and also be calculating d. D is nothing but e inverse of mod psi of n. Then I'll be getting a public key as e comma n or n comma e. My n over here is 33 and my e is 7. Again, my private key is nothing but it's the one that you already know, which is nothing but d is 3 have calculated by it, and n is nothing but 33. And I'll be sharing my public key. The public key is shared with the sender, and the private key is kept secret with the receiver. In order to encrypt the message, first I'll be, in case if it's in text message, I'll be converting it into this form. In case of ASCII form, or in a case of normal form, over here I'm just for the simplicity. Ciphertext is nothing but C is equal to M power E mod n. I'll be calculating it. Over here we have already know what is M. Just a second. Okay. Over here M is 13, and over here E is nothing but 7, which we have calculated earlier, mod N, which is my 33. And I'll be getting my ciphertext is 7. Over here my M, in order to get my decrypted message back, I have to calculate C power D mod N. Over here we have already calculated C as 7. 7 power 3 mod 33 is nothing but 343 mod 33, which is my 13. That's it. I hope you guys understand. So the core idea of encryption strength is that the time it takes to break it. So our security basically depends upon how fast the computers can calculate. In case of RSA, I'm taking you guys already know that RSA depends upon my prime numbers. My over here in case of RSA, n is equal to p into q. So I'm taking two prime numbers. If I'm able to factorize it faster, that means my RSA can be calculated faster. So the security is very less. So more complexity, slower performance. However, if there is less complexity, it's no more secure. As they get faster, we must increase the mathematical complexity. So there is a kind of, we have to balance our computational protection. Our security isn't absolute. It's kind of believed that the problem is too hard to solve. Basically, like, as long as that if someone finds a faster way to compute or a new kind of computer that can solve these steps entirely, every encryption system we use today could fail overnight. There's a possibility of it as well. So let's start with what quantum computing means. In a normal computer, every bit can be represented by with a definite state, either 0 or 1. However, in case of a quantum computer, it's exactly opposite. It can be represented by both 0 and 1 simultaneously. In case of, for example, in case of normal computer, everything you do, like encrypting a message or sending a message to your friend, only happens in a sequence. Sequence of zeros and ones, which is being switched on or off, this part. Now, in quantum computing, we replace these bits by qubits, quantum particles that can exist in a superposition of 0 and 1 at the same time. Let's take a scenario where, okay, imagine flipping a coin while it's spinning. In the air, it's both heads and tails until it lands. So that's superposition basically. But there is more. When qubits are entangled, they start behaving as in one unified system. Like one interferes in other. If there is a change in one, and other instantly reacts, no matter how much their distance is. This property lets quantum computers coordinate enormous amount of data simultaneously. Finally, through interference, quantum systems can amplify the correct solutions and cancel out the wrong ones, essentially letting physics itself to solve the mathematical problems by guiding wave patterns to the right answer. So unlike classical computers that test the possibilities one by one, quantum computers explores all paths at once. It's similar to breadth first such, like exploring all the paths and then just going to the next level. That's not faster computing actually. It's a kind of very different computing when compared to my classical computing. So these are the few visuals to explain what are the concepts of superposition, entanglement, and interference that we have seen earlier. So how quantum computing breaks the classical cryptography. Now that we understand what a quantum computer is, let's see why is it so dangerous for classical encryption. Our current security systems such as RSA or ECC depends purely on mathematical problems that take normal computers millions of years to solve. But with quantum algorithms, those same problems can be solved in minutes. In 1994, Peter Shaw developed an algorithm that uses quantum interference to factor large numbers exponentially faster. That means if someone builds a large enough quantum computer, RSA would collapse instantly. Similarly, Grover's algorithm accelerates brute force searches, cutting the effort to break symmetric ciphers such as AES in half. So what used to be secured by mathematics can be cracked in physics. This is an example for it. Yeah. Yeah. So the rise of material-based cryptography. Here's what material science comes into picture. To build quantum safe systems, we need materials that can preserve the quantum states and prevent noise or decoherence. Superconductors, graphenes, and topological materials allows electrons and spins to behave in controlled and stable ways. Without them, quantum encryption and communication would simply collapse. It's not just about the metamath, it's about the better matter. Superconductors enable stable quantum circuits. Graphene supports ultra-fast low noise signal transfer. Diamond NV center stores the quantum information, and topological insulators protect the quantum states from interference. Security is no longer lies in the mathematical or mathematical complexity. It now has been shifted into a picture of materials. Yeah, that's what I'm telling. The equation has been changed. Even the best algorithm, it's kind of meaningless if the hardware leaks energy or loses coherence. So we engineer materials that maintain stability, resist thermal noise, and physically enforce the security boundaries once left to map. This is where computer science meets the physics. So older equation was security is directly proportional to computational difficulty. Now it depends upon both the mathematical strength and also the material coherence. Both logic and matter now define the digital trust. Now let's move on to the superconductors, which are the foundation of the quantum circuits. Superconductors are the base material for the quantum chips. At temperatures near almost absolute zero, electrons flow freely without resistance. No heat, no energy loss. This stability is critical because quantum information is extremely fragile. Even a tiny energy loss can destroy a qubit state. For example, Google's Skymo processor, for instance, uses tiny superconducting loops to perform quantum operations safely and predictably. So we are not designing faster circuits. We are engineering matter that protects the information at the atomic level. In cryptographic systems, it's used to create low noise, high speed circuits that maintain coherence even outside of extreme cooling. It allows quantum signals like electron spin or photon polarization to travel cleanly without scattering. Researchers are even using graphene to generate the true quantum randomness, making it perfect for QRNGs, quantum random numbers generating. The building blocks of secure encryption keys. We already know what graphene is. It's a kind of an allotropy of a carbon. Topological insulators, the immune system of quantum data. This is one of the most futuristic area of material science. Topological insulators have a fascinating property. The interiors block electricity, but their surfaces conduct it perfectly. What makes them revolutionary is that their electronic states are protected by topology, a branch of mathematics describing geometry that can't be easily changed. That's what topology would basically mean, right? So even if the material has impurities or even has defects, the surface stays intact, making quantum bits much more stable. This is key to fault-tolerant quantum cryptography, where encryption literally can't be broken by noise or even damage or fault. Yeah. Now let's see how quantum computing breaks the classical cryptography. Now that we understand what a quantum computer is, let's see why is it so dangerous for classical encryption. Our current security systems such as RSA or ECC depends upon mathematical problems that can take normal computers couple of years to solve. But with quantum algorithms, those same problems can be solved in minutes. In 1994, Peter Shor developed an algorithm that uses quantum interference to factor a large number exponentially faster. That means if someone builds a large enough quantum computer, RSA would collapse it instantly. Similarly, Grover's algorithm accelerates brute force searches, cutting the effort to break symmetric ciphers in AES in half. Now, what used to be secured by mathematics can be now cracked by physics. Quantum hardware where matter becomes encryption. Classical computers basically use logical gates, which is a software level security. Quantum systems use physical laws, which is an hardware level security. Quantum hardware components, which is like superconducting Josephson junctions, form qubits. Graphene interconnects the carry quantum signals. Topological layers prevents decoherence. The result is, security isn't just computed, this is one of the most fascinating integrations of math and materials. Fully homomorphic encryption, which is FHE, which kind of means quantum chips. Let us compute, let us compute and encrypt the data. but it's so computationally expensive that normal hardware struggles. By using quantum safe materials such as graphene and superconductors, we can design FHE accelerators that handle encryption operations at cryogenic speeds. Imagine a secure AI model or cloud systems that never decrypt your data, even while processing it. That's a future of privacy preserving computation. Now let's see what is quantum key distribution is. Quantum key distribution, or QKD, is the first real-world example of cryptography powered by physics. It uses photons to transmit keys between two users. If a hacker tries to intercept or measure them, the photon state changes, and the intrusion is instantly detected. That's because the Feinberg uncertainty principle. Nature won't let you measure something without disturbing it. Today, QKD is already being used in a secure banking networks in China and Europe, enabled by ultra-pure optical materials like doped crystals and silicon photonics. We already know what is Feinberg uncertainty principle is. Del X del P is directly, is greater than or equal to h by 4 pi. Yeah. So, yeah. Next is quantum random number generators, QRNGs. Every encryption key kind of begins with a randomness. However, in case of classical RNG, random number generators, it's kind of pseudo-random, software based. In case of quantum, it's kind of it's kind of like truly random. It's a kind of physics based. The major idea behind is that you'll be generating from the unpredictable quantum phenomena, photon emission timing, electron tunneling noise, spin fluctuations materials. The materials kind of used over here is graphene photodiodes, diamond NV centers, and silicon photonics. No, there is no mathematical pattern, no predictability. Hardware accelerators for PQC and FHE. PQC and FHE are extremely secure, but they are very slow on classical processors. To make them practical, researchers are building specialized accelerators using quantum materials. Superconductors eliminate energy waste, graphene handles terahertz data rates, and spintronics enable near instant key operations. They aren't just chips, they are quantum safe engines that bring theory into real life performance. Cryogenic computing and side channel protection security at near absolute zero. When we think of hacking, we imagine software exploits. But at the hardware level, even tiny heat fluctuations can leak data. Cryogenic computing prevents that. By cooling materials below 1 Kelvin, electron movement becomes perfectly stable, no heat, no signal leakage, no side channels. This is how quantum cryptography hardware keeps data physically frozen, which is literally untouchable. Physically unclonable functions, PUF, basically means that no two materials, even from the same batch, are identical at the atomic scale. PUFs take advantages of these random variations. When you send a challenge signal to a chip, it's kind of unique. Its unique microscopic nature produces a response, that can't be copied or stimulated. It's like a digital footprint, not created by software but by the material itself. This means your hardware can literally prove its own identity. Okay. Hybrid quantum safe systems. Hybrid systems are how we will move safely into the quantum age. Instead of replacing the existing, encryption, we layer it with the new hardware. So even if quantum computers evolve faster than expected, your data is safe under two shields. One is mathematical, other one is physical. This is exactly how next generation banking, defense, and satellite networks are being designed today. Hybrid systems combine post-quantum algorithms such as Kyber lithium, quantum hardware, superconductors, spintronics, and photonics. One of the major benefits are multi-layer defense, seamless transition to quantum networks, long-term compatibility. We are using both math and matter, which gives us a quantum immunity over here. The next is, one second. Quantum security isn't too much distant from today. It's already kind of shaping industries. Banks are testing quantum safe ledgers using FHE and testing quantum safe ledgers. Doctors can process encrypted data using FHE and satellites. FHE and satellites are exchanging the keys using QKD. Next is quantum internet vision. So basically, imagine an internet where information is transmitted as entangled photons. Any attempt to intercept it instantly collapses the quantum state. Meaning, basically, eavesdropping, becomes literally impossible. That's the quantum internet, a global network where every you know connection is secured not only by password but also by the laws of physics. It is already being tested, between satellite labs and national networks in China, Europe, and US. So maybe like it's soon to be implemented in all our countries. So future equation. Until now, security was purely mathematical, but we have entered a new equation. It's not just about logic or computation anymore. It's about how stable your material is and how precisely you can measure its quantum state. In this equation, every term matters. Remove one and the system collapses. The strongest cryptography of tomorrow will be built only from these three, which is mathematics, material integrity, and measurement precision. Interdisciplinary career is the future. The fusion of cryptography and material science isn't just a research trend, it's a new career ecosystem. Tomorrow's cybersecurity experts will need to understand the quantum circuits, atomic lattices, and physical entropy. These careers combine coding with quantum design and math with material engineering. The frontier isn't just digital anymore, it's physical. Let's actually end where it all began. For decades, cryptography was pure math. But today, we have stepped into a new reality where the materials we engineer, where the materials we engineer, such as superconductors, graphene, topological insulators, define how safe our world is. Security is no longer about equations; it's about atoms, spins, and protons. The material has become the message, and the message is the future. We no longer calculate security; we just construct it. Thank you. Yeah. Bye.